Okay, this video will discuss the resistivity of metals at different temperatures. In the previous video, you've already looked at some fundamentals and important parameters involved in the flow of electricity. Okay, so here we have a table of the electrical conductivities of some metals and nonmetals at room temperature. Okay, so this is a standard information. Remember that conductivity and resistivity are related. Okay, they are the inverse of each other. Okay, and this symbol, the rho symbol, is resistivity. Okay, remember that rho is resistivity. So this equation allows you to calculate the resistivity of metals at different temperature, while the one given in this table is at standard room temperature. Okay, so we have the resistivity at temperature T. T is whatever temperature that we are currently working with, equals to, here we have resistivity at 0 degrees plus, times 1 plus alpha T times T. So alpha T is a coefficient of resistivity. This symbol is coefficient of resistivity. Okay, and T here at the end, capital T, is the temperature. So that relates to the temperature here. This is the same value. Okay, so if you want to find the resistivity at 40 degrees, for example, then it will be resistivity at 40 degrees equals to resistivity at 0. This is normally given, times 1 plus coefficient will be given times 40 degrees. Okay, 40 degrees because here is 40. So let's just go through one exercise to explain this, to apply this equation. So we have an iron wire to conduct 6.5 ampere current with a maximum voltage drop of 0.005 volts per centimeter. Okay, so it says a voltage drop, which we learned in the previous video that it's just V. But here you're given it in V over cm. So it's just like power in the previous example. You were given power per length. So this is actually volt or voltage per length of the wire. Alright, so what must be the minimum diameter of the wire in meters at 20 degrees Celsius? So very straightforward. We have current, okay, that we want to conduct. We have the voltage drop. Now we can take this as a voltage, and we can assume the length equals to 1 centimeter. If the length of the wire is 1 centimeter, the voltage drop will be 0.005. That's what it means. If the wire is 2 centimeters, then it will be 0.005 times 2, etc. So what must be the minimum diameter of the wire? So we have to find D at 20 degrees Celsius. Okay, so you have diameter, current, voltage, and length. Okay, so we are given information here. Resistivity for iron at 0 is 9 times 10 to the power of minus 6 ohm centimeter. It's given in ohm cm because it's easier for you to use. Okay, because everything is in centimeters. And then the coefficient of resistivity is given as this. Okay, so we can't use the resistivity value for iron at 0 degrees. In order to solve for all this, we have to find the resistivity at 20 degrees first, and then we use that resistivity value. Remember, resistivity is rho equals to Ra over L. Okay, we must find this resistivity at 20 degrees, and then we can calculate the diameter. Diameter will be given here. Okay, so you can write down the information that you have again. So we have current equals to 6.5. Voltage is 0.005 when length is 1 centimeter. Diameter is unknown. And what else? We need resistivity at 20 degrees. Okay, so before we apply this equation, because this equation is the one that will allow you to find diameter from the area. Okay, just analyze what information you have and what you need to find first. Okay, so we want diameter, we get it here. So to get this, we have to have length, which we have as 1 cm. We have to have resistance, which we currently don't have, but we can calculate because V equals to IR. We have V, we have I. And resistivity, we can't use the one at 0 degrees. We have to find the value at 20 degrees. So there are two things that we need to find before we find the area. Okay, so from V equals to IR, R equals to V over I equals to 0.005 volts divided by 6.5 ampere. 7.69 times 10 minus 4 ohm. Okay, if you use the standard units, volts and ampere, you will get ohm. Now we have R. What about the resistivity at 20 degrees? So we use the formula that we have from the previous slide. Okay, resistivity at 20 degrees is resistivity at 0 times 1 plus coefficient times temperature. Okay, so at 20 degrees equals to resistivity at 0 times 1 plus the coefficient of resistivity times the temperature. Okay, so just plug in what we have. Resistivity at 0 degrees is 9 times 10 minus 6 ohm cm, and multiplied by 1 plus coefficient is 0.0045 C minus 1, or degree C minus 1, sorry, multiplied by 20 degrees Celsius. Okay, should put a square bracket here. So let's check the units first. Degree Celsius, inverse degree Celsius will cancel each other out. Okay, so you will be left with, of course, the same unit for resistivity, which is ohm, centimeter, or ohm meter. Okay, so solve this. The answer will be 9.81 times 10 minus 6 ohm centimeters. So now we have resistance, resistivity at 20 degrees. We can calculate for area. So I'm going to rearrange that equation. Area equals to resistivity times length divided by R, 9.81 ohm cm, times length is 1 centimeter, divided by resistance is 7.69 times 10 minus 4 ohm. So check the units. Ohm will cancel out. Cm times cm will be square centimeters, which is exactly what we want because it's area. 0.0128 cm square. Okay, so the equation for diameter is area equals to pi d squared over 4. So from this, you rearrange to find diameter equals to, so 0.0128 times 4 divided by pi, and then square root, the diameter will then be 0.127 centimeters. Okay, so there are more questions after this one in the slide, so make sure that you go through them and that you actually try for yourself. Okay, the solution is there, but it's good if you try first.